Hello and good day everyone. In today's video, we'll be talking about the properties and characteristics of materials. Objectives: to be able to define engineering materials, identify its properties and characteristics, and knows the importance of studying engineering materials. So why should we study the engineering materials? Understanding the materials properties can help to better predict the manufacturing outcome. It is also important because we can know the efficacy of each materials in any field of services by knowing its properties and characteristics. Let's have first the definition of material science, the study of the properties of solid materials and how those properties are determined by materials composition and structure. It includes elements of applied physics and chemistry, as well as chemical, mechanical, civil, and electrical engineering. Engineering materials, the substances which are useful not only in the field of engineering, but in the day-to-day basis because of their properties and characteristics. Because we are dealing with engineering materials, we will be focusing on about metals. These materials enable people to explore in the new design and implementation of new products to improve the quality of modern life. Properties of materials. The term property is a qualitative or quantitative measure of response of materials to externally imposed conditions like forces, temperature, and etc. These properties includes physical, mechanical, optical, thermal, electrical, chemical, magnetic, and technological properties. So ito ang dapat nating malaman at dapat nating pag-aralan para malaman natin kung ano ang mga tamang materyales na gagamitin in any field or services. Now we have the physical properties of materials. Those distinguishing qualities or characteristics that are used to describe a substance in the absence of external forces. It is also the property that can be observed and measured without changing the composition of the material. So these are the common physical properties of material: the color, size, texture, melting point, boiling point, solubility, luster, density, magnetism, odor, viscosity, and the crystalline structure. But we will focus on the density, the melting point, thermal conductivity, electrical conductivity or resistivity, the thermal expansion, and the corrosion resistance of materials. First, we have the density. The formula is density is equal to mass over volume. So we are common with this and is defined as the mass per unit volume. It is derived unit usually used is kilogram per meter cube. Second, the melting point. It is the temperature at which solid become liquid at standard atmospheric pressure. As the heat is applied to solid, its temperature increases until it reaches the melting point of the substance or the material. So example for this is the tungsten, which has the highest melting point of all metals, and mercury is the lowest melting point. The third is thermal conductivity. It is the ability of a material to conduct heat. It represents the quantity of thermal energy flows per unit time through a unit area and temperature gradient as Q is equals to QD over A times delta T, where K is the thermal conductivity, Q amount of heat transferred, D is the distance between two isothermal planes, A is the area of surface, and delta T is the difference temperature. The common units used are watts per minute degree Kelvin is equal to the SI unit, or BTU per hour times feet times the degree Fahrenheit. Here is a picture which a conduction takes place. So as you can see, there are two isothermal planes, which is the path and the holder. The holder is which the conduction of heat takes place. Next is electrical conductivity or resistivity. It is defined as how much voltage is required to get an amount of electric current to flow. It also measures how strong materials can resist electric current. So napaka-importante nito na pag-aralan, especially by manufacturing or building an airplane or any other aircraft, because lightning could happen and the airplane and other aircraft must be electric proof para iwas aksidente or any tragedy. So the formula is R is equals to I over E times P, where R is the resistance, I is the distance, and A is the area of the sample, small p is the specific resistance, and the unit is ohmmeter. Next is thermal expansion. Thermal expansion is the tendency of a material to change in shape, volume, and area in response to a change in temperature. So here is the formula. Actually, it is alpha L. So alpha L is equals to 1 over E L times dL over dt, where EL or thermal expansion, L is equal to particular length, dL is equals to change in length, and dt is the change in temperature. The unit is equal to the coefficient of alpha A per degree Celsius. Last is the corrosion resistance. The last physical property of a material is the corrosion resistance. Corrosion is a formation of compounds on the surface of a metal when it is exposed to different environment. The common type of corrosion is the rust. Corrosion resistance can be defined as the ability to protect the substance from corrosion. In this picture, we have 4 objects that are exposed to an environment: the gold ring, copper tube, iron nail, and aluminum toy. So which object could get highly affected by corrosion? Probably you will pick the iron nail. Yes, you are correct, because iron nail is very reactive to oxygen and moisture that forms iron oxide. Therefore, the iron nail will corrode faster than the other objects over time. In order to protect the iron nail from rusting or corrosion, we have some preventions. These are the common corrosion preventions: the galvanization, coating the iron surface with zinc; electroplating, coating iron surface with other metal; and last is by painting. So these preventions create a barrier for the metals to come in contact with the oxygen and moisture, and therefore it resists corrosion or prevent the corrosion. That ends my topic, everyone. I hope you learned something, and the other properties of materials will be reported by my members. Thank you.
So this morning everyone, today we will gonna tackle about mechanical properties. Those properties which describe the behavior of materials under the application of the force are called mechanical properties. Such characteristics as strength, hardness, machinability, ductility, elasticity, and plasticity are included within this designation. These properties are great interest to the engineer who is called upon to select materials for machines and structures, and to determine the sizes of various members so that they will support loads adequately. So, mechanical properties is the strength or behavior of a material when there is an applied force, or for simple terms, mechanical properties of a material are those properties that involve a reaction to an applied force to a material. So it also can help to classify and identify the material. So, for example, so in product sheets and plate, the rolling direction is called longitudinal direction. The width of the product is called the transverse direction. the grain orientations, and standard growth forms of metallic products. So, as you can see, uh, the mechanical properties of a material are not constant in the oven. For example, temperature below uh, room temperature generally can cause an increase in strength of a properties of a metallic alloys, while its ductility, hardness, and elongation usually decreases. So, to furthermore discuss and explain what is mechanical properties, uh, there are six characteristics of mechanical properties that I included. First is the strength. So it is the property of a material which opposes the deformation or breakdown of material and presence of external force or load. Materials which we finalize for our engineering products must have suitable mechanical strength to be capable to work under different mechanical forces or loads. So it is strength of a material which is that there will no deformation, or in other terms, it is not uh, be cut easily or be deformed easily. So second is hardness. So the hardness of materials is defined as the resistance of a specific material to localized plastic deformation or indentation. The term may also be used to describe the resistance of materials to scratching, abrasion, or cutting. Engineering hardness is usually defined as resistant to penetration or machining. So hardness is a resistance. So is to not to do something, or to not be cut, or the hardness of a material which the difficulty of to be cut, that is the hardness of a materials. So machinability is the ease with which a metal can be cut, machined, permitting the removal of a material with the satisfactory finish. Materials with good machinability require little power to cut quickly, easily obtain a good finish, and do not wear the tooling much. So machinability of a material is a difficulty on which a material can be cut. So that is the simple terms of machinability. So ductility. Ductility is the ability of a material to sustain a large permanent deformation under a tensile load up to the point of fracture, or the relative ability of a material to be stretched plastically at room temperature without fracturing. So it's the ability of material to sustain a large permanent deformation. So sustain a large katason, or its long elongation of a material, of how much can he be stretched. So next is elasticity. When the external forces of a material are removed, the body returns to its original shape. The property of regaining the original shape upon the removal of external load is known as elasticity. So from its root word elastic, which means regaining, or capability of a material to to go back or regain to its original form or original shape. So next is plasticity. Plasticity is the property of a material by virtue of which permanent deformation can occur. Plasticity is really the opposite of elasticity. So from the root word plastic, or it's according to its meaning, permanent deformation. So it can be not regained to its original form or original shape. So that is plasticity. So that's all for the characteristics of a material. So in order to use engineering materials in design, fabrication, or construction, a knowledge of mechanical properties is necessary. These properties are determined in the laboratory under fixed rules of procedure which govern the art of mechanical testing. A mechanical test may be defined as one in which all the variables affecting a given property are controlled and the property in question is measured under fixed condition. The affecting of any variable upon this property can thus be specifically determined. So mechanical test is to test the ability or the capability of a material. So it is designed to ensure that materials are suitable for their intended application. So to its application of a material which gonna work for it. Or mechanical testing includes methods such as tensile strength, compression strength, impact resistance, fracture toughness, and fatigue. So mechanical testing is to test the capability. It tests the characteristic of material, which is I discussed lately, the strength, the hardness, the ductility, machinability, elasticity, and plasticity, and there are other more characteristic of material. So in simple terms, mechanical properties of a material is the ability or capability of a material to do something or to be intended for its application. So that's all for today's video, all about mechanical properties of a material. Thank you.
So, good morning, sir. My name is Darwin Oluza from BS Symmetry. So, my topic for today are about technological properties. So, what is technological properties? Technological properties are those qualities which give information regarding the suitable of metals for various technological operations or processes. Such properties are highly desirable in shaping, forming, and fabrication of materials. So, the following technological properties will be discussed. First is machinability. It is defined as the ease with which a given material can be cut, permitting the removal of material with a satisfactory finish at lower cost. It is used to signify how well a good finish. It may also be called finish ability. So, when we say machinability, it is a characteristic of a material such as metal that makes it easy to drill, shape, and cut. Materials with good machinability can cut with relatively little power and low cost. So, Second is weldability. So, weldability, it is defined as the capacity of a metal to be welded under the fabrication conditions imposed in specific suitability, design, structure, and to perform satisfactorily intended service. The real criteria in deciding on the weldability of a material is the weld quality and ease which it can be obtained. So, when we say weldability, it is also known as jointability. When we say jointability, it is the ability of any material to weld with the same materials. So, usually, we see materials commonly metal and alloy. So, it is two metallic parts, same or different metals mix and fuse when welded. So, that is weldability. So, for the third one is castability. So, the third one is the castability. So, castability, the ease with which this material can be cast into form is known as castability of the metal. It is based on factors like solidification, rate, gas, segregation, shrinkage, or etc. So, another one, when we say castability, it is the property of a metal which indicates the ease with it can be casted into different shapes and size. So the example of materials used is aluminum, brass, they are possessing good castability. So those two are good in castability. So for the last one is formability. So when we say formability, it is the ability of metals in forming of different shapes. The various factors which govern to a large extent the flowability or ductility of the metal are metal structure, grain, size, hot and cold working alloying, elements, softening heat treatments, and annealing and normalizing. So when you say formability, it refers to a material's ability to undergo plastic deformation. So when we deform a metal, heat is often used in forming process. So the very important about deforming materials is a correct temperature so the metal used are well formed and well built. So for our next topic is optical properties of general engineering material. So optical property deals with the response of material against exposure to electromagnetic radiations, especially to visible light. When light falls on a material, several processes such as reflection, refraction, absorption, scattering, etc. So, first is refraction. When light photons are transmitted through a material, they causes polarization of the electrons in a material, and by interacting with the polarized materials, photon lost some energy. As a result of this, the speed of light is reduced and the beam of light change direction. So, example of refraction is if you put a pencil in a glass of water, you will see that the pencil is bent in a water. It is because of refraction of light. So what is refraction of light? Refraction of light is the change in direction of light when it passes from the medium to another. When the light rays coming from the tip of the pencil pass from the water to air, they change direction. That is, they get refracted. When these refracted rays reach our eyes trace them backwards as straight lines. Due to this, the rays appear to come from the point slightly above the original position. Hence, the pencil appears bent in water. So that is refraction. So that is example of refraction. So the second one is reflection. So when a beam of photon strikes a material, some of the light scattered as the interface between that we media, even if both are transparent. Reflectivity R is a measure of fraction of incident light which is reflected in the interface. So when you say reflection, it is a wave bounces off surface when interacting with a material. For example, if you walk yourself in front of a mirror, you will see a reflection of yourself. Another is reflection of light. So it is change in direction of light or bouncing of lights from some surface, like the bulb bounces from the ground. Ground lights reflects off from the smooth surface. So that is reflection. The third one is absorption. When the light beam strikes on a material surface, portion of the incident beam that is not reflected by the material is either absorbed or transmitted to the material. The fraction of beam that is absorbed is related to the thickness of the material and the manner is which of photons interact in the material's structure. So, absorption is refers to a material taking of light and not reflecting it back. Example as when light strikes a black surface, it is absorbed by the surface and nothing is reflected. So when you say a leaf and a white light coming, you can easily identify a green surface. That is absorption. So for the fourth one is Rayleigh scattering. So her photon interacts with the electron orbiting around an atom. It is deflected without any change in photon energy. This is more vital for high atomic number of atoms and lost photon energies. Example, blue color in the sunlight gets scattered more than other colors in the visible spectrum and thus making sky look blue. So Rayleigh scattering is a wave dependent with a shorter wavelength being more scattered. From molecules, it is the atmosphere which gives rise to blue sky we see on a fine day. The blue light from the sun striking the upper atmosphere is scattered approximately 10 times more than the red light. So overhead, the blue light is scattered in the eye of an observer while the red light goes largely unscattered. So that's what we see that it is more that's what we see almost that the sky are always blue. So the fifth one is transmission. Transmission, the fraction of the beam that is not reflected or absorbed is transmitted through the material. Thus, the fraction of light that is transmitted through the transparent material depends on the losses incurred by absorption of and reflection. So, transmission, it refers to the passing of light through some materials. Example is when light passes through glass. When light passes through a glass of window, it is transmitted to the other side, allowing the light to pass through the window. Also, different materials have different ways of transmitting light. So, examples are transparent object. Transparent object allows you to see clearly through them, while translucent object only let some light through them. You cannot see clearly through translucent object. So for the last one is thermal emission. When a material is heated, electrons are excited to higher energy level. Is generally in the outer energy levels where the electrons are less strongly bound to the nucleus. These excited electrons, upon returning back to the ground state, release photons in process termed as thermal emission. So, when we say thermal emission, it is the processing involving the emission of electrons from the heated metal surface. So, thermal radiation is conductive via electromagnetic waves. As such, this is from a heat. This form of heat transfer is not only function of the temperature difference between the two surfaces, but also the frequency range of emitted and received energy. As an example, sunlight is composed of the visible light spectrum as well as infrared energy and ultraviolet energy. So that is thermal emission. So that's all for my report, sir, and thank you.
Good day, everyone. My topic is all about magnetic properties of engineering materials. So, magnetic comes from the word magnet. Are rocks or metals that create an invisible field around themselves. This field attracts other magnets and certain metals. So, we all know what this magnet is because we already see it in our surroundings. Magnetism, a physical phenomenon produced by the motion of electric charge, resulting in attractive and repulsive forces between objects. So, where magnetism, where the action takes place or the action happens, it's either attraction or the repulsion forces between two objects or more. Bohr magneton, magnetic moment due to spin of an electron is known as Bohr magneton or M sub B. The Bohr magneton, named for the 20th century Danish physicist Niels Bohr, is equal to about 9.274 times 10 over negative 24 ampere per square meter, where Q is the charge on the electron, H is equals to Planck's constant, and M sub E is equals to mass of electron. Bohr magneton is the most fundamental magnetic moment. The magnetic properties of materials, those which determine the ability of material to be suitable for a particular magnetic application. There are many magnetic properties of materials. The permeability, retentivity or the magnetic hysteresis, coercive force, and reluctance. The permeability, it is the property of magnetic material which indicated that how easily the magnetic flux is built up in the material. Sometimes is also called as the magnetic susceptibility of material. It is determined by the ratio of magnetic flux density of magnetizing force producing this magnetic flux density, denoted by mu. Hence, mu is equals to B over H, where B, the magnetic flux density is in material in Weber per meter square, H, the magnetizing force of magnetic flux intensity, and Weber per Henry meter. So, the unit of magnetic permeability is Henry per meter. Permeability of material is also defined as mu equals to mu 0 mu r, where mu 0 is the permeability of air or vacuum, and mu 0 is equals to 4 pi times 10 to the power of 7 Henry per meter, and mu r is the relative permeability of material. Mu r is equals to 1 for air or vacuum. A material selected for magnetic core in electrical machines should have high permeability so that required magnetic flux can be produced in core by less ampere turns. So, examples of electrical machines are refrigerators, washing machines, flat iron, and more. When the magnetic material is placed in external magnetic field, its grains get oriented in the direction of magnetic field, which results in magnetization of material in the direction of external magnetic field. Now, even after removal of external magnetic field, some magnetization exists, which is called the residual magnetism. This property of material is called retentivity or the magnetic retentivity of material. So, the hysteresis loop or the BHQ of a typical magnetic material is shown in the figure below. So, let us discuss first what is hysteresis loop. The hysteresis loop shows the relationship between the magnetic flux density and the magnetizing field strength. So, before that, what is magnetic flux? Magnetic flux is a measurement of the total magnetic field which passes through the given area. So, the loop is generated by measuring the magnetic flux coming out from the ferromagnetic substance while changing the external magnetizing field. So, let us discuss what is hysteresis loop. Hysteresis loop, B is the flux density in the upper, and the H is the magnetizing force, and the negative H is the magnetizing force in opposite direction, and S is the saturation in opposite direction, and P is the saturation. Looking at the graph, if B is measured for various values of H, if the results are plotted in graphic forms, then the graph will show a hysteresis loop. The magnetic flux density B is increased when the magnetic field strength H is increased from 0, which increasing the magnetic field where is an increase in the value of magnetism, and finally reaches point P, which is called saturation, point where B is constant. And with a decrease in the value of the magnetic field, there is a decrease in the value of magnetism. But at B and H are equal to 0, substance or material retains some amount of magnetism is called retentivity or the residual magnetism. When there is a decrease in the magnetic field towards the negative side, magnetism also decreases. At point C or the negative H sub C, the substance is completely demagnetized. The force required to remove the retentivity of material is known as the coercive force. And the opposite direction, the cycle is continued where the saturation point is S, retentivity point is T, and coercive force is U. Due to the forward and opposite direction process, the cycle is complete and this cycle is called the hysteresis loop. The advantage of hysteresis loop, a small region of the hysteresis loop is indicative or less loss of hysteresis. A hysteresis loop provides a substance with the importance of electromagnetic. So the coercive force, as we mentioned earlier, due to the retentivity of material, even after removal of external magnetic field, some magnetization exists in material. So, means the retentivity or the residual material. This magnetism is called residual magnetism of material. To remove this residual magnetization, we have to apply some external magnetic field in opposite direction. So, this external magnetic motive force, or the ATS, required to overcome the residual magnetism is called coercive force of material. So, the amount of reverse negative H external magnetizing field required to completely demagnetize the substance. So, this is how the coercive force works. So, the reluctance, it is the property of magnetic material which resists to build up magnetic flux in material. So, take note the resist. It is denoted by R. Its unit is ampere turns per Weber. So, reluctance of magnetic material is given by this formula. So, classifications of magnetic materials. The diamagnetism, paramagnetism, ferromagnetism, and ferromagnetism also have two subclasses, the antiferromagnetism and ferrimagnetism. So, diamagnetism, very weak from the word dia, very weak, exists only in presence of an external field. Paramagnetism, slightly stronger, with an external field is applied, dipoles line up with the field, resulting in a positive magnetization. However, the dipoles do not interact. The ferromagnetism, very strong, dipoles line up but impermanently upon application of external field, has two subclasses. The antiferromagnetism, dipoles line up but in opposite directions, resulting in zero magnetization. The ferrimagnetism, similar to antiferromagnetism but dipoles of varying strength cannot cancel each other out. The magnetism of dia, para, ferro, antiferro, and ferri, the magnetic susceptibility sign of dia is negative. Para, ferro, antiferro, and ferri are all positive. The magnitude of dia is small and constant. Para, small and constant also. And ferro, large function of H. And antiferro is small constant and ferri is large function of H. So examples of dia is organic materials because it cannot attract with the other metals. The superconducting materials. The para is alkali and transition metals, rare earth elements. And ferro, transition metals like iron. The antiferro is salts of transition metal elements. And ferri is ferrites and chromites. So let us proceed on the temperature effect. So temperature does have an indefinite effect on a material's magnetic behavior. So, with rising temperature, take note, magnitude of the atom thermal vibration increases. This may lead to more randomization of atomic magnetic moments as they are free to rotate. So, usually, atomic thermal vibrations counteract forces between the adjacent atomic dipole moments, resulting in dipole misalignment up to some extent, both in presence and absence of external fields. So, it depends on the temperature. As a consequence of it, saturation and magnetization initially decreases gradually, then suddenly drops to zero at a temperature called Curie temperature or the T sub C. The magnitude of the Curie temperature is dependent on the material. For example, for cobalt, 1120 degrees Celsius, for nickel, 335 degrees Celsius, for iron, 768 degrees Celsius, and for iron, 304 is 585 degrees Celsius. So the magnetic domains, in addition to susceptibility differences, the different types of magnetism can be distinguished by the structure of the magnetic dipoles in the region called domains. Each domain consists of magnetic moments that are aligned, giving rise to a permanent net magnetic moment per domain. Each of these domains is separated from the rest by domain boundaries or domain walls. Boundaries are also called Bloch walls, are narrow zones in which the direction of the magnetic moment gradually and continuously changes from that of one domain to that of the next. The magnetic domains are typically very small, about 50 μm or less, while the Bloch walls are about 100 thick. For a polycrystalline specimen, each grain may have more than one microscopic sized domain. Domain exists even in absence of external field. So magnetic domains, the average magnetic induction of a ferromagnetic material is intimately related to the domain structure. With a magnetic field is imposed on the material, domains that are nearly lined up with the field grow at the expense of unaligned domains. This process continues until only the most favorably oriented domains remains. In order for the domains to grow, the Bloch walls must move. The external field provides the force required to this moment, so it should be the Bloch walls to move so that the domains will grow. The magnetic domains graph, the y-axis is the magnetization and the x-axis is the magnetic field, where slope and the lower part is the initial permeability, and the center is the growth of domains. Slope is in the highest permeability, and the saturation is the slope is in the lowest permeability. So semi-hard magnets, once the area with a hysteresis loop represents the energy loss per unit volume of material for one cycle. The coercivity of material is a microstructure sensitive property. This dependence is known as the magnetic shift anisotropy. The coercitivity of recording materials needs to be smaller than that for others, since data written on data storage medium should be erasable. On the other hand, the coercivity value should be higher since the data need to be retained. So the soft magnet or the semi-hard magnet examples are hard ferrites, alloys, and soft magnets. Soft magnets are characterized by low coercive force and high magnetic permeabilities and are easily magnetized and demagnetized. They generally exhibit small hysteresis loop. Application of soft magnets include cores for electromagnets, electric motors, transformers, generators, and other electrical equipment. So examples, ferrous nickel alloy, ferrites, garnet. So soft magnets are temporary magnets. The hysteresis loop area is small, and the retentivity and coercivity is also small. So soft magnet can be produced by heating and gradual cooling. The hard magnets are characterized by high remanent induction and high coercivity. These are also called permanent magnets or hard magnets. These are found useful in many applications, including fractional horsepower motors, automobiles, audio and video recorders, earphones, and computer peripherals, and clocks. So, they generally exhibit large hysteresis losses. Hard magnets are permanent magnets. So examples are Excel, carbon steel, chromium steel, tungsten. A hard magnet can be produced by heating and sudden cooling. So that's all, and thank you.